This is a video me explaining how to use this factor of change method to solve problems that I call ratio problems. First, derive an equation for the quantity that you're being asked for. Replace each variable in that equation that doesn't change with the value of 1, and the variables that do change with the multiple of the change. So if you double the mass, you put a 2. If you triple the mass, you put a 3, so forth. Simplify and use that equation to calculate the factor of change. Then the new value will equal the factor of change times the old value. And that's this. It's so powerful if you can get this technique down. So here's a problem that I will apply this to that you've seen before. A projectile is launched vertically with an initial velocity of v initial, and that will go to some height that we will call h1. Now, a student doubles the initial velocity. What's the new height in terms of h1? So h new equals some number times h1. Does it double the height? Does it half the height? Does it quadruple the height? Obviously, I show you the answer. Now, how do you get that? What's the first step? We find an equation that gets the height equals something related to velocity. Well, this is an energy problem. So we have kinetic energy initial equals potential energy due to gravity final. And those two values must equal one another. Kinetic energy initial equals the potential energy due to gravity final. The initial kinetic energy is equal to 1/2 mass times the initial velocity, which we call VI squared, which must equal the potential energy due to gravity final, and we called that H1. And we're interested in how all of these changes impact the height. So solve for H, mass cancel. H1 is equal to, we got 1/2 V initial squared, and then we have to divide by G. That was the first step. So we have an equation relating to the variable or for the item that we're looking for and whatever physics principle is involved. And then we're going to look and see what happened. Well, what did we do? We doubled the initial velocity. So we're going to calculate a factor of change, and we're going to focus on this equation, and we're going to look at each variable in that equation for height and ask ourselves, did it change and by how much? 1/2 is a constant, so 1/2 doesn't change. Velocity initial did change and it was doubled. So I'm going to put a 2 there, but notice it is super important. Velocity initial was squared, so I have to square the factor by which it changed. And little g is a constant in both problems, and so little g is replaced with the value of 1 since we didn't change the planet, which I could have changed the planet. So the factor of change is equal to 4. So the h new is equal to the factor of change times h old. So h new is equal to 4 times the original height. And that's how I got 4. May seem silly, but trust me when I tell you, it is a powerful approach. So I'll just kind of draw that off to the side, and we will now apply that to a problem that is more AP specific. The magnitude of the gravitational field on the surface of a planet is 2 times little g. 2 times little g, their meaning is 2 times g from Earth. 2 times 9.8 is what they're asking or referring to, because they're going to compare this planet to Earth. So we have Earth, all the values for Earth, and we have this new planet. What is the planet's radius in terms of Earth? We want to know the radius of the planet equals some number times the radius of Earth. Okay, that's what they're asking for. Now, this is a ratio problem, I call it, or an opportunity to apply planet factor of change method. What do we know? We know that little g on Earth is equal to the big G times the mass of Earth divided by the radius of the Earth squared. And what we're asking is we want to know what happens to the radius of this planet. Okay, so rearrange this equation for radius. Radius is equal to big G mass of the Earth divided by little g on Earth, and we'll take the square root. And so we'll call that radius of Earth, and we'll call that little g of Earth. Okay, now let's calculate this factor of change. We're going to focus on all the things that are in this equation for radius and ask ourselves, does it change? Big G is a constant. Well, did the mass of this planet change? Let's see, the planet's mass is 1/2 the mass of Earth. So we're just going to put the half in, and that's the factor by which the mass changed. And did little g change? Well, they told us that it was twice g, and mass was half the mass. So I got to put a 2 in for g. So 1/2 divided by 2 is the same as 1/2 times 1/2, and that becomes the square root of 1/4. Square root of 1 is 1, and the square root of 4 is 2, so the factor of change is 1/2. So the radius new is equal to the factor of change times the radius old, which is the radius of the Earth, and the factor is 1/2 times the radius of Earth. And so the answer is B. Now, number 3. This is the hardest, what I call ratio problem, that I have seen on an AP exam. I used to do it by developing an equation for one item, developing the equation for the other, and then dividing the two. And it took me 20 minutes to do the math on this without using factor of change method. So I just will tell you that you're going to need the volume of a sphere equation, which is on the front sheet of your AP green sheet. And you're also going to need to know that density, which I also think is on the front page, is equal to mass times volume. So we're going to refer to that in just a minute. We have a newly discovered planet. So here's my planet. It is said to have a density, which, by the way, density is equal to m over volume. That is the equation. It's called rho. It looks like a p, but it's rho is equal to 2/3 the density of Earth. So it's not quite as dense as Earth, so it won't have the same mass as Earth. In addition, the radius of this planet is twice the radius of Earth, so it's larger in diameter. So even though the density is less, now I have a larger radius, so I don't really know how mass is going to get changed. And they want to know the surface gravitational field. What are they asking for? Little g. That's what they're looking for. So I have this situation over here. This is Earth. We know that little g on Earth is equal to big G times the mass of Earth divided by the radius of Earth squared. Well, the first step in a factor of change problem is to have an equation for the item that we're looking for. So here's the equation. We're looking for the surface gravitational field, which is a little g. So we're going to calculate the factor of change on little g. So look at each item. Big G. Does big G change? No. Does the mass of this planet change? Yes. We don't know how much it changes. I'm going to come back to that because we have to figure that out. It's almost like a double factor change problem. Does the radius of this planet change? Yes. They told me that the radius is twice that of Earth. So there's 2. Now I've got to deal with this change in mass. Well, we know that the density is equal to the mass divided by the volume, and we want to know mass. So I'm going to rearrange that for mass. Mass is equal to density times volume. Well, the problem is that we have volume changes because we have a radius change. So I'm going to plug in for volume the 4/3 pi r cubed, and I'm going to calculate the factor of change in mass. Does the density change? Yes, it changes by 2/3. Does 4/3 change? No, that's a number. It's a constant. Does pi change? No, it's constant. Does the radius change? Yes, they told me the radius doubles. I'm going to put a 2 in there. Don't forget to cube it. The factor of change related to mass is 2/3 times, 2 times 2 is 4 times 8. 2/3 times 8, that's 2 cubed, that's 16/3. So the mass nu of the new planet is equal to the factor of change times the mass old. Well, it's the old planet was Earth, so it's 16/3 times mass of the Earth. Now I know the factor by which the mass changes, and I can go and plug in the 16/3 up here. 16/3. So the factor of change on the radius, which is where we were at, I'm sorry, on G, excuse me, um, is 16/3 divided by 2, which is the same as 16/3 times a half. So that's 16 times 16/3. Uh-oh, did I do something wrong? 16/3. Um, what's my problem? 6. That's 6. So I'm feeling like I did something wrong here. Hold on. Ah, I know what I did wrong. I forgot to square that. Let's do it again. Don't forget to pay attention. See this the radius was squared in the original equation. You have to square the factor. So 16/3, and then I have a 4 on the bottom as well. That becomes 16/12. Now again, what am I finding the change of? The little g. So g new is equal to the factor of change times g old. So it's 16/12. Well, that's g on Earth. So 16/12 times 9.8 meters per second squared, and that'll equal 13 meters per second squared, which, by the way, is a Newton over a kilogram. There's your answer. Okay, that is the factor of change technique to solve ratio problems.